I'm gonna introduce Dr. Greg Zacharias here. He's worked his entire career at the intersection of humans and the increasingly complex and autonomous systems they use. As a young Air Force lieutenant, he worked on the flight control system for the space shuttle. In 1983, a few years after he completed his PhD, he co-founded Charles River Analytics, a company that creates custom intelligence solutions ranging from autonomous robots to large-scale C2 systems. More recently, he served as the chief scientist of the Air Force and released just last month a book that came from that effort, Autonomous Horizons: The Way Forward, which discusses challenges and recommendations for the Air Force's next steps in autonomy. He currently serves as the chief scientist for DOT&E, which you all probably know. That's why you're here. Among other duties, he is leading the Artificial Intelligence Test and Evaluation Working Group, which stands at the intersection of the T&E community and the AI and autonomy community. So today we look forward to a discussion of what the way forward looks like for T&E of emerging technologies like AI and autonomy. Welcome, Dr. Zacharias.
Thank you so much. Thank you. Okay. So thanks everybody. Thanks Heather for the intro, and thank you all for lasting here with me between now and Miller time. Appreciate it. So I'm going to give you kind of my overview of emerging technologies and the implications for test and evaluation. But I'm going to do a little bit of a bait and switch on you. I'm going to talk first at the high level of what the office's major focus areas are, and then kind of dive down into one particular area that's near and dear to my heart. So I'm going to first want to talk a little bit about these 8 areas that are of high interest to the director and to our office. First is dealing with software-intensive systems. Mr. Beeler came from the Software Engineering Institute, and he always says software is going to define more and more of the functionality of these systems and also open up the attack surface as well. We want to shift left, as you heard Mr. Dare this morning, working with combined DT, OT, and even requirements up front for testability. We want to improve our test infrastructure and ranges so they can account for these new technologies coming on board and make those investments. We want to recognize the importance of human systems integration. This is one of my favorite pictures of a Predator ground station. This is really the cleaned up version. If you actually look at what they really do, there's just an entire mess in there, and we're stuck with an engineering system 20 years ago. Increased modeling and simulation throughout the system's life cycle, from initial requirements to all the way to logistics and sustainment with digital twins and the like. Assessing reliability's impact on sustainability. We know where the real costs are on the logistics tail, and there's tremendous savings by increasing reliability. Adapting T&E, which is the title of this talk, which I'll get to emerging technologies, and maintaining an agile workforce, and seeing if we can all stay as young as Tom Cruise in Minority Report. So let me talk about the T&E of these technologies. And talk about a number of them, but I'm only just going to touch on a couple. We know hypersonics is coming down the road, plenty of money coming into it, directed energy as well. We may have, because of these new technologies, or they're really not new, but because of our investments now, new problems. It's not just range and speed with hypersonics. We've got maneuverability, material science, all kinds of fundamental issues to deal with. Same thing on the DE side. Quantum computing, let's just introduce another level of uncertainty in the things we're trying to test and see what kind of fun we're going to come up with. Nanomaterials, clearly some interesting issues to do with material science, reliability, and so forth. And then finally, autonomous systems. I'm going to touch on these comments, but we know they're going to be complex. They can fail in multiple ways. They may be learning and certainly working in non-deterministic ways, which I'll touch on shortly. We're going to be needing new approaches to this. So let me focus on autonomous systems. and some of these issues. First, I want to talk a little bit about why, because not just because they're there, but um, um, why we're talking about it. And this has been ongoing for probably the last 5 years, certainly with this um, notion of a second and third offset. We know our adversaries has caught up with us on stealth and precision weapons and so forth. We need to start moving forward. We know our adversaries already have, um, but so we need to do some leapfrogging in terms of our weapon systems concepts and how we develop them. So there's also a technology push. You all see it in the commercial world with vehicles, with go-playing games, and so forth. And it's not just the algorithms that have happened recently. It's certainly the hardware platforms as well, and lots of infrastructure, Metcalfe's law, um, uh, and Moore's law, and so forth that are helping us make these things cheaper and more effective. And finally, the benefits. We talk about robotics platforms, undersea vehicles, land vehicles, air vehicles, and so forth. We tend to think about these platform type solutions, but really my feeling is that the greater benefits are going to be in the information processing side of it, in terms of automating the AOCs, for instance, space centers, and really getting to multi-domain joint coalition operations. And really getting us, if you think of ourselves, we shouldn't be thinking of ourselves as platform manufacturers and operators. We should be thinking of ourselves as an information-centered service providing organization with exquisite peripherals on the outside there to take care of things. So, and I think one of the major things that's going to get us to an information-centered focus is these autonomous systems. So. This caused us to work on a study for the Air Force for a couple years. I'm going to give you kind of a sense of it. It made us really think hard about definitional issues, and I've been in multiple studies where we sat around for weeks at a time trying to define what is and what isn't autonomy. You can start thinking in terms of formal definitions from the dictionary. It's easier to think in terms of working with your subordinates and your peers in a human relationship where you give them a limited scope of authority and then let them go forward and do their job and not micromanage them, for instance. Likewise with a team member. So I've been working with a very simple kind of notion of defining this for machines, basically telling them what to do in terms of goals and objectives, or a mission from a military side, telling them what not to do in terms of constraints on behaviors or rules of engagement, if you will, from the military side, and then finally the whys of why you gave them that goal, and those are really we would call that commander's intent. But really not getting into the details of how to do their job, and dealing with unplanned for situations in the weather or the adversary and so forth. So it's a pretty simple behavior-based definition. And the other thing I talked about just before is recognize that these are systems that can be either in motion. This is Craig Fields, the chair of the Defense Science Board, back in 2012, made this distinction because we were focusing too much on the vehicle side of it, platform side, and really think about the at-rest applications too, cyber warriors, logistic systems, and the like. So that's as far formal as I want to get on this. And I'll certainly be happy to take questions on that at any time. But so I want to say, so getting there, how do we get to these systems that can do these kinds of tasks that we'd like to give them? I think the time is right, as I said before. Why aren't we moving more quickly? And this is kind of a, yes, Mrs. Lincoln, how'd you enjoy the show kind of thing. But, we're scattered, we're stovepiped, we're duplicative. lacking critical mass. But what else is going on? And the question is, we get hung up on defining the terms as opposed to worrying about their behaviors. And the issue is, can we bring these different communities together to work together with common frameworks and architectures? And you're going to hear me argue for this, obviously. If I've got a question up there, I'm going to try and answer it that way. But and then really, when we build these things, what are the key T&E issues that we're going to face when the development community, the requirements community put these out there? So, and what can we do from a systems design point of view, as well as developing T&E tools and processes? So, I mentioned this Air Force study. It's recently published, and it's on autonomous systems development. And I want to be the first to admit it's very heavily focused on the development side and not the test and evaluation side. But my feeling is that the behavioral objectives that we're calling out on the development side will support the T&E community in the test side, and then could also serve as a roadmap, or guidance really, for a roadmap in T&E development. So the study itself begins by outlining a series of behavioral objectives dealing with three things: proficiency, trust, and flexibility. So I'm going to go through them with you. First, in terms of, we're calling them properties for proficiency. We got 4 of them. One was situated agency. Realizing that these should be agents. They have sensors. They take in information from their environment. They see, think, and do, if you will, and then they go and act on the environment. In fact, sometimes they may act on the environment first for discovery purposes to see what the environment is, and then go get the sensory input. But whatever it is, it's really a closed loop system. Second is adaptive cognition, doing things differently for different types of problems. You think about IBM Watson having hundreds of small algorithms working in parallel, voting systems and so forth, working on the problem in concert, or maybe switching depending on the proficiency of these subsystems. I think we're also going to have to deal with multi-agent emergence as these systems work with one another. We're not just talking about simple flocking, but much more sophisticated interactions across these systems, and worrying about what, and that's clearly going to be a T&E issue coming up. And then finally, learning over experience, and we focus really on experience of an individual autonomous system, but there's also the kind of learning that you find fleet learning, like is embedded in Tesla right now. When one vehicle learns something about a pothole being there, it transmits to the rest of the fleet, and so you have basically cultural learning in effect. So we believe these will help us. Some of these issues will help us in the T&E world too, and I'll talk about that. But assuming we could build these systems with these behavioral properties, is that enough for getting them out on the field and using them? And we would say no. I think what we really need to worry about is human trust in these systems, and think about that. So we know they can lead to high regret actions in our military. It's not just losing a game of Go or misjudging someone's weight or whatever the test is. And we know that trust will severely impact how these things are used. If I mistrust it, I won't use it. If I overtrust it, I'll get into trouble. You'd like the Goldilocks level of trust, the appropriate levels. So there's a huge literature in human trust. I'm sure many of you are aware of it. And there's lots of factors that drive the level of trust a human will have in another human. Is that person proficient? Is that person compromised or not failed, if you will? Is that person dependable? Are they reliable over time? Are they predictable? Do I have a sense of what they're likely to do? Can they give me answers in a timely fashion or an anytime response in effect? Do they reduce my uncertainty or do they increase my uncertainty? All those kinds of things um, influence how we trust people. But clearly, there's other barriers to human-machine trust, and the fundamental one is they don't think like we do. We've got mental models of each other, and we can probably go on that, but they can't explain themselves. They have low self-awareness. They don't know when they're violating their operating envelope, like the MCAS. Certainly didn't know that it had a failed sensor on board that we heard from Mr. Dare this morning. I'm sorry, Jared Freeman at lunch. So these are all issues that will influence trust. And so what happens if you've got low trust? You end up the humans end up behaving as if they're in a Harry Potter movie here. That I can't figure out what they're doing. So we felt that we needed something on the order of something catchy, tenets of trust. We want to put out in this and talk about, again, 4 of them. And I'm just going to talk about them very briefly. In other words, we'd like some congruence in a cognitive sense with how these systems think with how we think. Now that can be done sometimes architecturally, sometimes algorithmically, and sometimes never. And if that's the case, you'd like to have some approach to understanding their reasoning. If they can explain to you, there's a couple DARPA programs now, XAI, Explainable AI, trying to take a unexplainable deep neural net notion and turn it into almost like an old-fashioned 1980s expert system, explanatory system like that. So, or you'd like to be able to drill down and say, why did you say that, or why did you decide that, or why did you give me that advice? But just like you would do with a subordinate if you got some information like that and you weren't quite clear. Second, you really need these systems to have situational awareness. They need to know about the environment around them. They need to know about their own health. They need to know where they are in the operational envelope, so that they know that they're on the edge of their own proficiency. Third, you really do need to these. We talk about autonomy all the time as if they're in a vacuum out there somewhere in middle space. They're going to be working with humans all the time. Whether you launch and it's a fire and forget system, someone launched it, you're the controller of it in effect, or you're acting as a teammate during a mission, however it works. So you need communications, natural language processing, other things like that, and then also if you're working as a team, you need to know mutual goals that are going on and who's going to complement who or who's going to correct whom. And then finally, to build this up, it does take training and working together mutually, where I'm working with an autonomous system, building a mental model of its behaviors, and ideally vice versa. It's building a mental model of me, and really this is how we do teamwork anyway. It's training. So in addition to these, we circle back to the basic needs of the basic reasons we're using these systems. It's not just to save money or to do the dull, dirty, dangerous. It's really to be flexible in what they encounter, as opposed to automatic systems, which end up being brittle. Eventually, they break at some point. So really, we need to drive flexibility. And we've got 3 dimensions of flexibility that we'd like to see, both how they deal with different tasks, how they can change them with the goals that are taken on, and the approaches that they take towards dealing with those goals. We talked about this adaptive cognition earlier, and that's really enabled by a bunch of these other items that I've got listed up there in terms of task sharing and learning from experience and so forth. The second is peer flexibility, where it may be serving as a team member, maybe serving as a subordinate to you, or sometimes it may be serving as a superordinate, a supervisor, where it may be an advisor in the AOC, basically generating flight plans for a human out in the field, which is a little cantankerous from my colleagues in the Air Force, but I think we're going to find more advisory systems that are working that way. And it'll be, instead of, we talk about humans in the loop and humans on the loop, well, this may be humans under the loop. So think about that. And then finally, cognitive flexibility, you mentioned this earlier, is how changing how a task gets done differently and carried out, and again enabled by some of these other fundamental components of adaptive cognition and learning over time. So we've got and I just wanted the peer flexibility. I just want to illustrate that's a good example of that is with the auto GCAS that will provide a pilot with safety if the pilot's forgetting that they're getting close to the ground, and it will do an auto take over of the aircraft and then resume authority to the pilot once it's in safe area. So that's changing that relationship. I've got a cartoon here of trying to say that these were the properties for proficiency on the left-hand side and the tenets of trust on the right, and then driving these principles of flexibility. And down at the bottom there is this, what we're calling autonomous behavior, with the needed flexibility for taking over these systems, the trust in using them, and actually serving proficiently in doing them. So I'll just summarize these three dimensions of behavioral. I'm not going to read them again. It's proficiency, trust, and flexibility. And so these are really the behavioral objectives that ought to be designed for these. I think the point I'd like to make here is that these are also supportive of the T&E of these systems, that they can be transparent, for instance, in why they're making these decisions. If they can be flexible, if they can be proficient, that's really good for us too. So, and I think some of these will, and I'll suggest how some of these will help us in the T&E world. But the other thing that should help us in terms of doing the test and evaluation is a second major category of recommendations we made in the study in terms of frameworks and architectures and platforms. So I believe there's a convergence of communities across there, and I'm going to illustrate both in the AI world, cognitive science world, neurosciences, and so forth, that they're really different communities, but they're talking about the same thing if you start looking at it pretty deeply. And I think that there's an opportunity to build common frameworks across these communities in terms of computational models of perception and reasoning and planning, the R&D to get these operational benefits, different lower level functions, and then techniques for implementing those functions. I'll go into that. And then finally, platforms. I mentioned earlier about the technology push that we have now. We've got cloud computing, we've got Moore's Law still working for us, and ability to do layered architectures at the implementation end. So let me just talk about this convergence of communities, which I do believe, and this is another cartoon here, but I think we've been doing robotics for about 120 years, believe it or not. We've been doing cybernetics, which is Earl Wiener's notion of making the same kind of mathematical models for humans and systems since the 40s. And I think they're helping us get better ideas on how to do human system teaming and to actually make mathematical models of those. On the lower part, we've got the neurosciences. I mean, literally, we just discovered the nerve cell back in probably the 1890s. It hasn't been that long, and realize, and especially with fMRIs and so forth, we're getting huge insights into how the neurosciences support cognition and the mental models that have been almost separately developed by the cognitive psychology communities, and people are building cognitive architectures. We heard earlier today about ACTAR being used at University of Arizona State, sorry, and these kinds of things bringing computational life to these architectures. And then finally, what's hitting the newspaper is stuff that started probably in the 40s, both the hard AI, the semantically oriented, logical, symbolic type of computing, and then around the same time, really, it was a neural network starting, and then falling out of favor about 3 times, I would say, since the 40s and now it's back up on another hype curve. But providing us with incredible abilities to do both symbolic and sub-symbolic computation, which I think are going to give us an ability to do computational models of humans and cognition, as well as 4 systems that will allow us to build them in similar ways and give us a common framework, and that should be plural. Obviously, there's no single framework, but to build these frameworks that will give us a broader scope across applications and get us out of this stovepipe that we find now. So let me give you one example, and this is clearly from my block diagram sense of the world, but this is the cartoon of the independent autonomous system, inputs, outputs, talking to the outside world, people, other machines, red and blue machines working together or against each other. And then just imagine if you took the lid off of that center block of the autonomous system, and this is one of my crowning achievements of getting this animation to work. There we go. Okay, good. So I don't know if you can read it, but I've just, this is a very block diagram type of architecture. There's other architectures out there, but going from left to right, you've got inputs from the outside world, driving sensors, you've got databases, you've got sensor and data fusion going on, and then you've got, I dare not, no, maybe I'd try that. There we go. And then you've got this inner situation assessment, decision-making layer, which is really the essence of these machines thinking, doing situation assessment, decision-making, planning, execution, and execution monitoring until you get some outputs in the effectors, and then they go around to that, imagine that cloud back down there in the previous diagram. And then from the top down, you've got HCI inputs for the humans to team with at multiple points in the processing. You've got learning going on down at all stages if you want, or any single stage. And then you've got a domain-specific knowledge base layer which separates the algorithm, the procedural knowledge from the declarative knowledge, if you will, separating out that kind of information so you can go and reapply all or parts of the architecture to other domains. So, and then finally, underneath is a whole set of toolbox and technologies. So, like I say, this is just one example of a potential architecture. There's certainly others out there. But the notion is that by doing this kind of separation of functions into architectures, you can go and take these kinds of functions that were just in the previous block and go and break them out into enabling technologies where you can go and have people working, communities really working in parallel on hard AI approaches, soft ones, traditional methods like estimation and control, and machine learning and so forth. So the notion is separate out the technology development from the functions that are being implemented. And then the other part of this is to go and set up an architectural patterns. So you've got again, as in the previous diagrams, you've got the HCI up on top. You've got some set of architectures here. You've got the functions and computational methods. And then finally, you've got the actual hardware software platform. And this itself may be 7 or 8 layers if it's any kind of modern software hardware architectures. And then you've got the actual interaction with the outside world. But this whole notion of layering these systems allows you to separate efforts, work in parallel, and again, avoid the kind of monolithic systems that we build in DoD now that really slow us up, certainly for revisions or anything like that. So this just summarizes that kind of thing. Go for the architectures, work on these technologies, and then work in modern commercial type environment with these multi-layered hardware and software architectures. So clearly, by separating out these functions, it should help our T&E efforts because of the modularity and the notion of where the connections occur. So I'm going to touch on a couple T&E issues. This is really work in progress now, but we're in the process of reviewing a number of studies. I don't want you to read these, but this is just the last dozen years or so. Although there's a 2004, but so they're pretty up to date. There's probably at least 3 times as many as these that I'm familiar with. There's lots of work just in the T&E area, not autonomous systems in general. That's what these are focused on, and some of them, that are repeating now, and people are recognizing the same problems over, and so they really need to be categorized. But let me just try and identify a few of the issues that are being raised here, and I'm sure some of you are familiar with these. So these are kind of the I'll call the dark clouds of the issues facing us. So we've got dynamic, unpredictable environments that we're deliberately putting these systems into. We've got non-deterministic behaviors that are coming out of these systems, or that these systems they're actually characterizing these systems. We've got a lack of understanding of the internals of these systems. Again, hopefully with the transparency in design, that will be ameliorated. We've got these, people call them astronomically large state spaces, where formal methods are probably going to fall on their face unless something happens new in terms of that kind of approach to software validation. This is an issue. Instrumentation, we don't have the orange wires through these systems, and no one really is designing them for testability. And I made that comment in one of our meetings, and I think it was Kristen said to us, well, no one's designing for testability for any of our systems, so so what? So I think this is one of the reasons we've got to get, as a T&E community, get involved in right up front in the acquisition requirements and start putting that in there. So we've got an inability to specify these requirements at an operational level. If you go back to the definitions I had for autonomous systems, you're really talking about high-level operational intent, not low-level micro physical behaviors like speed and altitudes. We also have got to recognize that we tend to think of a capability gap, and then a ConOps, and then a system that's going to get rid of that capability gap within a ConOps. Here we need to have ConOps co-developed with the technology as we learn the capabilities of these autonomous systems, and that's going to make testing really interesting. Yes. Oh, I'm sorry. Is that? Oh, I'm so sorry. Okay. Is that better? Okay. My apologies. Okay. Never mind. Okay. So, and we've got requirements, traceability throughout the acquisition part of things. I've mentioned this before, we're lacking frameworks. We're doing one-off mom and pop opportunities all around the DoD, and with no coherence at all. And that's going to give us problems on the T&E community, because everyone is going to be a unique one-off. We don't have the ranges to test these systems. We don't have the test beds, and certainly we don't have the personnel that we need in the numbers we need. We've got subjective risk assessments that are going to uninformed by data. We don't know how to bring that test data into real risk assessments with these systems. Again, I mentioned emergent behaviors and dealing with learning and both pre and post fielding. We've got problems there. And then certainly I talked about the human systems integration issues and the human trust. And at some point, we're probably going to get to the point of these systems worrying about the trust of the human that doesn't have as much information as this particular autonomous system may have. And there's probably other stuff I forgot to put on the list. Okay. So with these black clouds, I think I mentioned some of these could be dissipated a bit with the design approaches we proposed earlier, but there's still other things that need to be done. And some bursts of sunlight. Unfortunately, these look like little TNT explosions the way I drew them. But so we've got operational requirements. How do we take operational requirements at the high end and decompose them down lower and lower and lower to the modular level? We don't know how to do that. But if we could do that, it'd be fantastic. Design for testability is a great thing. And transparency, explainability, I think I talked about that. And then if all else fails, we'd like to have runtime monitoring. This may be, looking at the envelopes and making sure that these systems stay stuff. You end up in these recursive homunculus kind of questions, but if the systems are simple enough, maybe we can build these monitors. We need sequential T&E throughout the development cycle at the very earliest concept phase, and this goes with that digital thread. We've got to have the M&S to support that as well when the system doesn't exist. We need aggressive modeling and simulation at all stages, and we need to figure out how to co-develop ConOps with autonomous systems development, and that really says you've got to bring in the operator from the get-go. And which we're all kind of believers on. And then finally, we've got issues with cyber vulnerability, and I didn't have room to put that on, but that's counter autonomy. I'm on a counter autonomy defense science board study right now, so we're already trying to figure out how to defeat these systems, certainly how blue can defeat red, but we also want to defend against red defeating blue. We want to look for new methods for dealing with emergence and learning, improved statistical engineering methods to deal with these dynamic systems. And then finally, this I mentioned before, how do we do this data-based development of risk assessments? And one of the studies suggested not only do we need data, but we also need to analyze the argumentation that went into the inferences made. In other words, what is your logical flow? And we need to make sure we can analyze that. So as I mentioned, we've formed up a board to bring together the practitioners here that are mostly you folks in the room with the S&T folks that are developing these systems, because I firmly believe we need to understand how these systems work if we're going to test them effectively. And certainly we need more S&T in the methodology, and then we've also got to bring the acquirers into the room. There's no question about that. So with that, I'll say thanks to you all, and I'll put up this org chart since I was suggested I do that. So there's a okay. So there's a question of consistency. So I think I have about 2 minutes for questions. Anything? I got.